Number 27. The left ventricle of a resting adult's heart pumps blood at a flow rate of 83 centimeter cube per second, increasing its pressure by 110 millimeters of mercury, its speed from 0 to 30 centimeters per second, and its height by 5 centimeters. All the numbers are averaged. Okay, great. Calculate the total power output of the left ventricle. Okay, so basically now, in terms of understanding what these values mean, this is simple. This is the volume flow rate, right? So the 83 centimeter cube per second, that is Q. Now be careful. Remember, Q, we need cubic meters per second. So let's just get that out of the way. So here we have 83 centimeters cubed per second. To convert that into meters cubed per second, centimeters on the bottom, meters on the top. Do not plug in the cubed yet. This is 100 centimeters for every meter. That is a known quantity. Now what you will do is you will cube the entire ratio. Okay? Please do not do this. As you're plugging this in, don't do cubed here, then do 100 to 1. That would be wrong. You could plug in a cubed here and a cubed here as well. That's fine. But I suggest you do it this way. Centimeter to meter, know the rate, know the relationship. You know that there's 100 centimeters in a meter. And then this whole thing, just cube it. Okay? Now this is easy. In terms of then getting our value, it's basically 83 divided by 100 cubed. All right? So this is 83, then divided by 100 raised to the third. And here we now have, this is going to be 8.3 times 10 raised to the minus 5. And that is in terms of meters cubed now per second. I know there should be 3 sig figs there, but I'll take care of it at the end. Okay, now that's good. The next thing is it says it increases its pressure by 110 millimeters of mercury. So first of all, we need pressure in terms of Pascal, right? So that's going to be the first thing. So how do we convert millimeters of mercury into Pascal? You can remember the conversion. You can do it. There's a whole bunch of ways to do it. But let's just do this. 110 millimeters of mercury, and for every 760 millimeters of mercury, there are 1.013 times 10 to the 5 pascals. All right. The reason why is because both of these are equivalent to 1 atmosphere, and since they're both equivalent to the same thing, they're both equivalent themselves, right? Just a little logic. So 110 multiplied by 1.013 times 10 to the 5th, divided it by 760. And here we're now going to have a value of 1.47 or so times 10 raised to the 4th Pascal. Okay, so those are the units in Pascal. Now this pressure, just so you know, is coming from essentially the contraction of the cardiac muscle itself. So let's pretend this is the left ventricle, all right? And what happens is the cardiac muscle of the left ventricle contracts. And when it contracts, it reduces the volume, all right, of the left ventricle. Now, when it reduces the volume, what happens, do you think, to the pressure inside here? Well, it goes up, right? You know the relationship. You know, if you think about this, what about if you squeeze the balloon from all sides? What's going to happen to the pressure? It goes up. So basically, pressure increases when volume will decrease, okay? So hopefully that should make sense. So basically now, what I'm trying to show is that this value here, the increase in pressure, is the P1 in this equation. I'm going to use this equation because they're talking about power. And I have a lot of variables changing. They said the pressure changes, the velocity changes, and the height will change as well. So, okay, so we talked about this now. That's going to be basically P1. Then they also tell us its speed goes from 0 to 30 centimeters per second. Now, they don't have the delta values in here, meaning it doesn't show you change in velocity here, it just says V2, but really it should be delta V, okay? And this should also be delta H, okay? And also this should be delta P. They should all be change values. So in other words, right, it says increasing the pressure, so this is really your delta P, okay? It changes its speed to 30 centimeters per second. Oh, and look, isn't that wunderbar? They gave us it in centimeters per second, so we got to do another conversion. So 30 centimeters per second times now, we got it in meters per second, centimeter on the bottom, meter on the top, 100 centimeters for every 1 meter. And we realize that it's going to be 0.3. I'm just going to leave it there. I know it's sig figs, whatever. This is meters per second now. Okay. This is now your delta V. Okay. And the height, right? So they gave us the height again in centimeters. This, again, just divided by 100. So the height in meters now, is going to be 0.05 meters. Okay? And this now is equivalent to your delta H. So again, this is delta P, this should be a delta V, and this should be a delta H. Now we have everything we need, all in the appropriate units. Okay? And here, by the way, is our Q, so all I'm doing now is just literally plugging it into this formula. So P1 was 1.47 times 10 to the fourth, plus then 1/2 times the density of blood, right? The density of blood is just slightly larger than that of water, so it's going to be in terms of cubic meter, in terms of, kilogram per cubic meter, it's going to be 1,050. You can look that value up if you like. The velocity then, the change of velocity was 0.3. That's going to be squared. Plus now, again, the density of that fluid, which is still blood, so that's 1,050, times then gravity, 9.8. Now it says it also increases height. All right, so the signs are important here, because if it increased the pressure, but let's say decreased the height, then this would have been a subtraction. Okay, so just be careful. Everything has increased, that's why everything's staying positive, but in case the problem changes on you, now you know. All right, if the pressure said it decreased the pressure but increased the height, this would be a negative, this would be a positive. Anyway, multiplying it by now the positive change in height, so this is going to be 0.05. And now we have to multiply this whole thing by Q, right? So now take that, multiply it by 8.3. Let me make that a little neater. 8.3 times 10 to the minus 5. And voila. Just let's throw it into the calculator. So we have 1.47 times 10 to the fourth plus 0.5 times 1,050 times 0.3 squared plus now 1,050 times 9.8 times 0.05, and then that whole thing now multiplied by 8.3 times 10 to the minus 5. We get a value of approximately 1.27, right? 1.27, and this is in terms of watts. You could have left it in, or not leave it in, but you could also do joule per second. It doesn't matter to me. They're all the same. All right, so this should be pretty close. I mean, the only approximations, I use the approximate values here and here. So the answer might be, you know, a little, it might be off by in the 100th place, but you get the idea. Guys, thank you so much for tuning in. We appreciate it very much. Please remember to subscribe, and we look forward to helping you out with more problems. Take care.